So, welcome to Mathematical Universe once again. We can continue on the endeavor to now prove the equation of tangent to a parabola. We know this is a parabolic equation, right? So I'll just repeat it here. Y squared equals 4ax. Now, the first thing we are going to do is to differentiate it implicitly. So to differentiate implicitly, let me write it. Now, when we differentiate implicitly, we are saying we are going to add ddx of this expression. That is, we are saying ddx of the left hand side and ddx of the right hand side. So it means I'm saying I'm looking for the differentiation of y squared and differentiation of 4ax. Now, we know the differentiation of y squared with respect to x will give us 2y dy dx. So I just want to use another pen here. 2y dy dx, right? You understand the reason why I'm using another color of pen as time goes on. So this differentiation of this is going to give us 4a because ddx of x is 1. Then with this constant here to come out, so it's just like you're saying 4a d dx of x. So this dx over dx will give us 1. So that's why we'll be left with 4a in this junction here. Now, the major thing is now to make dy dx is subject to the formula. Now you can understand why I use the red pen to differentiate them. Now, to make dy dx remain here, it means I have to multiply both sides by the inverse of the coefficient of dy dx. What do I mean by that? I'm saying that I'm multiplying this part and this part by 1 over 2y. So this can nullify this and I'll be left with dy dx here, and whatever I do to the left hand side I do to the right hand side. So it means this cannot nullify this. Then dy dx can now be 4a over 2y. At this junction here, we know that 4 divided by 2 will give us 2. So 2 here is 1, 2 here is 2. So dy over dx will give us 2a over y. 2a over y. But hold on, at points x1, y1, something is going on at point x1, y1. At point x1, y1, I just have to replace whatever expression I have here. So it means dy dx will be 2a y1 at point x1, y1, because the initial equation is mostly at the origin. That is, the vertex here is at the origin. But at this place, the vertex is not at the origin. We are looking at it in different parts of the Cartesian plane. So now, if the equation of tangent at point x1, how will it look like using dy dx? We are saying that at point x1, y1, this should be y minus y1 over x minus x1. You should know the equation of a slope at one point, right? Being equals to, so I just change this expression to this. So this and this are still the same, equals at one point. So 2a over y1. Now when we get here, we can now cross multiply. That is, I'm saying this expression multiplied by all this expression, and this expression multiplied by all this expression here. So to cross multiply, we are saying y1, sorry, I think the camera went off that time. So the last part was saying that the y dx is equals to 2a over y1 at points x1, y1. Then I was saying that the y dx is same as y minus y1 and x minus x1 is same as y minus y1, x minus x1, then equal to the function it was carrying before. Then the next step is to cross multiply. When we cross multiply, we have y 1 into y minus y1 equals to 2a into x minus x1. So move it forward a little. So at this place here, we can multiply this with this. This with this will give us y1y. This multiplied by this will give us minus y1 square equal to 2a multiplied by x will give us 2ax minus 2a multiplied by x1 will give us 2ax1, right? So at this place here, what can I do? I can just change this one to write it properly the way we used to write it. I can rewrite this as y1. That is, I'm bringing this y at the back here to the front, so it becomes y1 minus y1 square equals 2ax minus 2ax1. Now this y1 square, we can work on it. Let us go back to the very beginning. At this place here, this is just the equation of a parabola at the origin. But if it's not at the origin, what will be the equation of this parabola? So if the equation of the parabola is at x1, y1, what will be the expression? So the expression of this at x1, y1, that is, we are saying that since x1, y1 is on y squared equals 4ax, this implies what does this imply? It implies that instead of writing this, I can write it as y1 squared equals to 4ax1, right? Now it means this y1 squared can represent this whole expression. Let's even call this equation 1 here. I'll call this equation 2. Then I can say substitute equation 2 in equation 1. If I substitute equation 2 in equation 1, it means I'm bringing wherever I see y1 square, I'll substitute with 4ax1 in this place here. So this is equation 1. So this becomes y1 minus, this time around I cannot write y1 square now. So y1 square is already 4ax1. So it's going to be 4ax1 then equal to the equal to here, then 2ax minus 2ax1. Alright, so now we can do away with this bracket here and take this expression to this side. So this can be written as y1 equal to 2ax minus 2ax1, right? We have the 2ax and 2x1 here. Then this one that I'm transferring here, it is negative. When it comes, it becomes positive. So plus 4ax1. Then you take note of something. You see that this expression and this expression are the same. That is, this and this are like terms. And if they are like terms, this is more like we are saying 4ax1 minus 2ax1. It will give us 2ax1. 4ax1 minus 2ax1 will give us 2ax1. So this will now become y1 equals 2ax positive, because this minus this will give us positive 2. It's just like 4 minus 2 is 2. So 2ax1. Then what do you notice is common here? We notice that 2a and 2a is common. So because they are common, we can bring them out. Alright, y1 equals 2a into what will remain when we bring them out, x plus x1. Now this expression here is known as the tangent to a parabola, or to the parabola. Thank you.